Okay, good. So the part of the talk is related to the skin system. We have already seen yesterday quite many and today talks about the motivation for doing the lap on skin to monitor ECG or different kind of vital signs or harvesting, many things. We are mainly interested in our university to measure the pulse wave. And how we are going to do that? It is to build up an ultra-thin system where we have a sensor system over here, pre-amplifier, and then we have an ultra-thin piezoelectric sensor. So by doing this one, we can diagnostic all the wave and the morphology of the pulse wave signal, and that is extremely important if you really want to understand something what is inside of the let's say blood circulation system. So we are aiming on CBDs, detecting certain features. So when we are doing this research and really going on the clinical side, it is extremely important on these lab-on-chip systems that they are really accurate. So that is one of the things that you really need to repeat and see that the sensors that you are developing can actually be comparable with the medical devices that they have in a hospital. The other part for the user is definitely the user contact. So you really need to, and how we are doing that one, the idea is to build up ultra-thin devices. These are going to be then conformable. So the sensor stack that we have over here, it's less than 5 micron in a thickness. So what we have here, we have inverter, which is connected. So this is the P-type inverter built. Then we have the resistor and capacitor over there for the loop. So we have the charge amplifier. So that is the part of today's talk. And then the other part, if we have time, I'm trying to be really fast now. We can also discuss shortly about the pulse wave detection. And one of the things over here is the thermal stability. When we are talking about the polymer semiconductor devices, we all know that they are not so stable in terms of temperature. So this is the fabrication process shortly. How we do this, we have a glass wafer coated with the relief film. Then we are having the CVD process to apply the parallel C on top of it. We use an inkjet printer to make the connections, the gate and the capacitor electrodes, another layer of parallel over there for the capacitance as an insulator layer, and then also for the gate. Then followed by a source drain and top electrode, as well as the connections to the resistor. And then we are dispensing a surface energy band in order to control the flow of the active materials. For that one, we use for semiconductor, you see the materials for the resistor and semiconductor over there. And then we can finally release these ones. And what does it look like? You see that one shortly over here. Resistor, transistor, and the capacitor. So all the elements that you can find also over here. These are the cross sections. Quite nice control. Some challenges in fabrication, and I think the biggest challenge is when we have these ultra-thin films, how these are actually being transferred onto the skin. So as I said, one of the questions or the challenge is that when we start increasing the temperature, here we have the VTC measure. So for the inverter, the blue one, so here we have 21 Celsius, and then when increasing the temperature, we see that the threshold voltage of the inverter changes, as well as the gain decreases quite a much, I must say. When heating from 21 to 60 Celsius degrees, these measurements are down with, if I do remember correctly, 10 millihertz linearly increased voltage. So, as said, both here, oh, doesn't show that. Okay, well, you see a little bit different picture on the paper. So You can look more carefully on the confidential intervals over there. They should be seen here, but I don't know, maybe something wrong. So a couple of points on this slide. As you can see, the gain as well as the threshold voltage of the inverter both decreases as a function of temperature quite much. So maybe then the question is that is it going to be a problem? In first time, we would think yes, it is quite dramatical change. But then let's take an example. So in this paper, we made a simple thermal modeling where we have a skin which was placed on a constant temperature of 34.5 Celsius degree. Then we have the parylene, and then we have air with normal convection on the other side. We placed the started to change the thickness of the parylene over here to a little bit understand what will happen. And once we are increasing the thickness, let's say it's 1 millimeter, then we can the temperature on top of this parylene increases somewhere 38, 40 Celsius degree if the ambient temperature is at 60 Celsius degree. So then if you are looking devices that are here, ultra thin, let's say less than 10 micron, less than 5 micron, as I said, then it's basically following up only the temperature of your skin. So it doesn't sound actually so problematic. So here, for example, really thin, small increase in the temperature. So then thinking about another point. So this was the two graphs from the last slide. You remember the gain and the threshold. And then we are from Finland, so we love to do sauna. And let's take mild sauna, that's something like 70 Celsius degree. And if you are there even like 30 minutes, your skin temperature actually increases like only 6 Celsius degree. So if we are taking that one into account here, then you would stay in a sauna with this one. The temperature of these devices, they actually increases only like 6 Celsius degree. And I kind of, so basically, this is showing that the body itself is cooling the device. You really don't need to consider in all applications, like skin applications, you don't need to take these ones into account. It's actually there by its own. So shortly then, some results also from our pulse wave measurements. So how we are doing this one is that we are printing top and bottom electrode. We are using an MIM kind of a structure. Over here, the plate coat PVD TRFE, and we are polling that one with a quite high voltage. And with that one, we can reach quite good sensitivity. Typically for the PVD TRFE, the sensitivity is something like a little less than 30 picocoulombs per Newton, the charges that it can produce. But in case if you make these ones thin, and that is shown in the paper over here, if you make those ones extremely thin, you can get new kind of a bending modes, new kind of modes of generating charges, and that will generate something like even 1700, so 50 times more, 1700 picocoulombs per Newton. So with that one, you can get extremely nice sensor devices. And we have monitored several patients. They are young adults, mainly students, but then we had also measured some patients. The thing that I want to emphasize here is that we can really detect all these nice features. We compared these ones with the Finapress, which is a commercially available medical device for detecting the pulse wave. And we can at the moment recognize like stiffness index and radial augmented index as the clinical index that they typically use. And then a few things about the amplifier. So we have that nice signal so that we measured with the sensor itself. We use that one to feed through the sensor system. Then you get a little bit noisy. It starts generating noises when we have these. But if you have delicate signal processing, a few filters taking mainly out the 50 Hz noise, then again you get quite nice signal back, and you are able to identify. Here we have 25 different cases that we analyzed. We get a really good, let's say, values in terms between before and after. So not too much changes throughout the whole process. So with that one, I used my time, and I want to conclude that these kind of pre-amplifiers can be used already, especially for the body monitoring. And the reason is that in your body signals, they are typically from 2 Hz, or in this particular case, you need to go to 10 millihertz or something, up to 30 Hz. So that is the bandwidth that you need. You really don't need a high frequency transistors in order to do biosignal analysis, especially in the pulse wave case. And I want to thank the funders, European Union, Academy of Finland, and definitely the collaborative partner in Japan to help us to make all this. And having said that, I want to thank you. And if you have any questions, more than happy to answer.